is saying that yes, because I was as a kid saying that seems kind of absurd. It said yes, one of the possible paths is a particle starts off, goes the opposite direction, goes down to the corner drugstore, goes around the clerk 3 times, and comes back. That's a possible path, and that's one of the he was trying to illustrate saying that's one of the infinite paths that a particle can go from going from A to B. But it said that they can do the calculations because most of those more so-called ridiculous paths tend to cancel out, and what remains is the shortest possible trajectory between 2 points.
Now these are possible.
Except when you get in.
I mean, there are paths that are just not possible, or as you said, most of them will cancel out in some way, right? Because they're based upon wave
functions. When you're trying to calculate everything, the functions around all these absurd paths.
Yeah, it's like a quantum mechanical analog to the principle of least action. I mean, the integrals do involve the Hamiltonian operator, and you pick up a phase, which will sort of describe your final amplitude for these ridiculous paths, and you get a lot of cancellation from the math. You get these handy dandy e to the minus.
Now, one of these days. Oh, sorry.
And then e to the positive I to the such and such, and there's a lot of cancellation there, and you get it's a lot. There's a lot. I could talk forever about that stuff. It's a wonderful subject, and one of these days I do want to get somebody that I know. Her name's Jade. She did a wonderful presentation on this particular thing, and I wouldn't mind getting into some of the more complicated things because I have a very, very basic understanding. Like all I know about a Hamiltonian operator, and you're probably gonna laugh at me, but as far as I understand it, the only thing it is basically like the Hamiltonian of a psi function is equal to the basically different states of the energy of the psi function. So basically, they're eigenvalues and eigenstates of possibilities. That's the only way I can possibly relate a Hamiltonian operator because I've never really worked with them. Yeah,
but they are related somehow to the different ways you can have energy relating to your psi function, something along those lines, eigenvalues and adding vectors together for transformations.
Yeah,
I'm explaining it really poorly. Maybe you can kind of clean that up.
Me or Landon?
You.
Yeah, so you could think of the Hamiltonian as like a propagator. It's T plus V, your kinetic energy plus your potential energy, and then remember the Lagrangian is the kinetic energy minus the potential. But here we have T plus V, and so you could write down these quantum mechanical operators that essentially depend on Q, which is your coordinate, like X, Y, Z, your position, which is related to potential energy of the system. And you could write down the first time derivative of the coordinates Q, which give you your momentum. So you have P and Q, which are these sort of non-commuting operators. And so you might remember those two guys from the uncertainty principle, delta P, delta X. So they like to pair up. And so you have them both showing up in the Hamiltonian operator. And you essentially add up all the possible paths, and they're weighted by the phase which pops out front, and you do these integrals, and you get so essentially the Fourier transform. So it's interpreted as a matrix multiplication. The sum over all states integrates over all the Q's and takes the Fourier transform in Q, the change basis to P. And so the action is on the Hilbert space. You're talking about the Hamiltonian propagator and phases that ultimately determine the amplitude. And so you get a lot of cancellation, and you get the more probable paths. You can still have multiple paths that the particle could take, but you may not have all the ridiculous ones happening regularly. You'll still have a bunch of them that are possible to go from A to B, but it doesn't necessarily all cancel out to just one path. So you add them all up, and it's all normal. We
can probably make a whole presentation on each of those, right? I mean, we can go into Fourier transformation. The only thing I remember, I did work with Fourier, but that was basically going from a frequency domain to a time domain. Lagrange, I remember kinetic energy minus potential energy. Is that right? But yeah, no, I think that each one of those could probably spend about, a whole 2 hours just talking about different way to do transformations, but they're all based upon matrix theory of some way. They're all talking about different vector spaces and Hilbert spaces that you mentioned. But the path integral formalization, so this right here is a lot different than the way quantum GR looks at it, right? GR looks at a single shortest geodesic path, but the loop quantum gravity looks at an infinite number of paths, basically, right? And then takes a summation and then finds the best possible path. Okay, next. So the way I would describe a wave function, and again, I'm going to turn over to you guys, but a wave to function is something that describes a system. You have the psi, which is your wave function, and your psi squared, which is the probability density. And the way that I kind of relate them is that if you have a wave function, that's going to give you, let's say you have a standing sinusoidal wave, like shown in the little diagram there. Let's say the first, we'll call that the first fundamental, and the second would be the next. So in this particular first fundamental, you would have a wave, a sinusoidal wave, right? That's the top half of a sinusoidal wave. And the probability density is basically the likelihood of finding a particle at a given position given that sinusoidal wave. So at the maximum amplitude of that wave, that is the area where I would most likely expect to find like an electron in an orbital. Think of it as a range that electrons could exist with respect to the nucleus. So they're in this bounded condition. We'll call them the s orbital or the p orbital or the d orbital. But they're bounded in such that you're not going to find an electron in a transition zone. You're going to find a very low probability of finding an electron near the point where the sinusoidal wave starts to meet the x-axis. But as the sinusoidal wave reaches its maximum, that's to be the most likely place you're going to find an electron. And in quantum mechanics, the electron is everywhere. It's existing the entire spectrum of that boundary, and it's not even at a specific point until this is actually observed, which is another thing that's quite distinct from what we see in macro scale. So the second one would be that sinusoidal wave. Each one of those is basically, the top part would be, again, where the particles more likely to be found. The null would be where it hits the x-axis. So this is a relationship between the probability wave density and the wave function. Now, maybe you can kind of like expand upon that a little bit. Matter of fact, Athena, you want to take this one? You dealt with this one a little bit.
Yeah, I'll jump into this one. So branching off of actually what we spoke about just before this, it ties in well with this because, as you said, that there's two different behaviors happening when it comes to the macro scale and then the quantum scale. And so this is extremely important because we notice when observing quantum particles and the way that they behave, there's something known as a double slit experiment, where this, I'm just going to relate this for a moment. This is actually about a pathway, two different pathways, and shooting specific quantum particles through it. And they noticed that there was a whole scattered range of locations that the particles would hit on the backside of the double slit experiment. So this showed that its journey was all these different possibilities, right? Like you said, the path integral formulation were all these different possibilities. And whereas with general relativity, and as you see in this first wave function, there's just one main possibility, whatever is the shortest distance to get from point A to point B. And so the reason that this is important, and we're applying this obviously to the macro scale, is if you can find a way to make the mathematics in both formulas work together in one combined formula, then we may be able to actually figure out, okay, if this is how quantum particles behave, then maybe this is how the early universe might have behaved, to actually find, it's like an elimination process to find out which path did our universe take either before the Big Bang or just after the Big Bang. So again, I know I just kind of tied it all into the bigger picture, but with this, that's what's so great, and why wave functions are being looked at on a topic like this specifically, because obviously there's wave functions of everything. And so I think that with trying to look at the cosmological scale, but on a quantum scale, so quantum cosmology is very, very important in something like this to figure out just what happened before the Big Bang.
Yeah, I like that you tie it all together because the no boundary kind of does treat the universe as a quantum object. And I think it was Dr. Kroon I was telling before. I was talking about what's called a principle of supervenience that's in philosophy. And the principle of supervenience is basically that lower things affect higher structures. So even the smallest things will seem to be able to have very similar things as you go higher up. And so these waveforms and wave functions and probabilities, even though they only happen at the quantum level, do have macroscopic analogies in some ways.
Yes.
So, and you can talk about matter waves and things of that nature. So, but anybody else want to add on this one? Or is that kind of just a very basic way of looking at wave functions?
Good fun.
So
good.
I'm going to
yes, good.
I'm going to resist the urge to go down the double slit experiment rabbit hole because that's a whole talk.
We could do a whole presentation on that, couldn't we?
Yeah.
I love the double split. Yeah, the double split.
It's so
good. and as
I
say,
that would be fun. We could do something like that.
The triple split experiment and multiple slit experiments. Actually, it's one of Feynman's early recording talking about asking questions about that.
Have you seen the triple experiment where they have a photon goes in one, goes back through it in the middle, and comes out the other, basically?
I did not see that.
It's bizarre. It's really bizarre. The path that it took corresponds to basically going through one, coming back through the middle, then going out the other one. It's really strange.
Sounds like a crazy Saturday night right there.
Yeah, weird things happen in quantum. Again, not what you would expect in the macro thing. But again, even in mathematics, you can have weird things happen, like the Tarski paradox. So you can have like one thing form two. But anyways, that's gonna be on tangent. Next slide. By the way, it took some effort to try to distill this stuff down to the most basal way of explaining it. So I'm gonna like making it too simple, but at the same time, I'm hoping I don't go over his head because basal approach, just basics, just the bare minimum to understand wave functions, right? I don't know how much more simple I could have made that.
I like it. I think you did a great job.
Yeah.
Okay. Because it's not easy. It's not easy taking and distilling a bunch of stuff down. I mean, we all had wave mechanics. Wave mechanics is not easy. Okay, it sucks. And to try to get wave functions down to explain how the angular momentum and propagation and phase and velocity and all that stuff, it's confusing. And so I had to what's the most easiest way to explain this? All right, so we're going to talk about real quick the normalization of a wave function. Because again, I think that if you go look at the no boundary proposal and something like that, you kind of need to understand how you do a normalization of a wave function. And basically, normalization is basically the wave function with respect to the position and time. If you look at the psi xt, that's a function. Whenever you see like f of x, it's a function of f of x. So this it's a wave function with respect to position and time. And the wave function normalization accepts the fact that a probability must exist between 0 and 1 at any given point, such that the total probability of the system is 1 that the particle does exist somewhere. So if you look at that wave function in the prior screen, where you had like the single amplitude of the sine wave, the single half of it, between the intercept on the y-x-axis, the first one and the second one, there's a probability of 1 that the particle is in that area. It has to exist somewhere in there. Now, at each point in there, it's a probability anywhere between 0 and 1. But the total summation, and you could use the normalization integral, which is basically just saying on an integral from negative infinity to infinity, with the probability density, right? The whole wavelength of the density of these particles has to be equal to 1. And so you're just normalizing it to 1. That's where it basically means to normalize it to me. And there's other normalizations out there too that Dr. Kroon could probably get into as far as eliminating infinities, but I think that's kind of way more complicated than we need to get into. But would you say that this is basically just a simple way of saying that we want everything to equal to 1 to normalize it?
You guys have
things
to be
that
really
exist
careful.
Have a probability of existing of 1.
Yes. Dr. Kroon, what were you saying?
Yeah. You guys have to be real careful. If you're going down a sketchy part of the neighborhood at night, you go down a back alley and there's a guy in a trench coat that goes, "Psst, you want a probability density function? I got it real cheap." You're going to get ripped off because he's going to give you a non-normalized probability distribution function. It's useless unless it's normalized. So you gotta be careful for people trying to.
So this is why I'm trying to relate to people. These things only really kind of have use to us if we can normalize them. And so I wanted to think of a way. What's